Now we'll do another example. We will calculate the force exerted by water on a submerged plate. This time, the plate is in the shape of a right triangle, as we can see here. So for this example, the plate, we suppose, is submerged so that its top vertex is 2 meters submerged below the surface of the water. The plate has a short vertical leg of 5 meters and a long horizontal leg of 10 meters. So what is the total force exerted on this plate by water? Again, we will use the fact that the pressure exerted by water at a point which is d meters deep is given by rho times g times d newtons per meter squared, where rho is the density of the fluid, water in this case, g is the acceleration of gravity, and d is, of course, the depth below water. That's what we'll use. So again, the challenge here is the fact that we'll do so one horizontal strip at a time. We can assume that the pressure is constant across the horizontal width of the strip. We can also assume that if the strip is of sufficiently small height, a height of, let's say, delta y, that the pressure variation from the top of the strip to the bottom of the strip is small enough to ignore. And therefore, we'll be able to calculate the total force on this plate by multiplying the pressure times the area of the plate. Well, the area of the plate will be the length of the plate times the height, which is delta y. The length of the plate, however, will vary as we move down the rectangle. So we need to find a precise description of how this length varies as we move down the rectangle, the triangle. Moving down the rectangle will be controlled by a variable y, which will describe our depth below the water's surface. Of course, right here, y starts out at a value of -2 for 2 meters below the surface. And down here, y ends at a value of -7 for 7 meters below the surface. So let's see how we can describe this horizontal length in terms of, or as a function of, depth y. To do so, we'll take our triangle and we'll position it carefully in the xy plane as follows. Here's my x-axis and y-axis. Here's my triangle, and I have depicted or drawn a typical horizontal strip along which we'll calculate the force. And we've also, well, let's go ahead and carefully label these, the x and y coordinates of these points. This top vertex has x coordinate 0, y coordinate -2. Down here we are at x coordinate 0, y coordinate -7, and over here x coordinate 10, y coordinate -7 as well. And we can use these coordinates to write the equation in slope-intercept form of this line, which coincides with the vertex, with the hypotenuse of the triangle. And that's important because we want to measure the distance from here over to here, the length of this rectangular strip. Well, that length is essentially the x-coordinate of the right endpoint. And that x-coordinate is found in this equation. We can solve for x in terms of y, or in other words, we can invert this relation to write x equals -2y minus 4. And to do that, we just took this first relation, the equation, the slope-intercept form, and solve for x. That's all we did. You move the 2 over, multiply by -2, and you solve for x. So there we go. Now the nice thing about this relation is that it tells us exactly how wide our strip is at a depth of y. And you can test it out and measure it. For example, if y is, say, 3 meters deep, or if our strip is 3 meters deep, then the y coordinate down here is y equals -3. And if you plug in -3 to this expression right here for y, you get -2 times -3 minus 4, which is +6 minus 4, or 2 meters in length. And that seems plausible. Now, if you go all the way down here to the bottom of the triangle, the depth here is y equals -7. You plug in -7 to this relation, again, and you obtain -2 times -7 minus 4, which is +10. And that's precisely the length of this leg here at the bottom of the triangle, 10 meters. So that's a good expression for length in terms of depth y. So we'll use that now in our expression for the total force on this plate right here. Now again, to be a little more general, we'll assume that we're calculating the force on this plate, which is at an arbitrary depth of y below the surface. So our force is given by the pressure at a depth of y times the area of that strip. Now the pressure at the depth y is given by rho times g times depth right here. Now we do have to be a little careful with y here. We are measuring y below the water's surface, so y takes on negative values, but depth of course is a positive quantity. So to get this positive pressure, we need to multiply rho times g times negative y. That negative sign in front of there takes into account or cares or corrects the negative sign of y that's built into this coordinate system. So there's the pressure in the area. We've left it a variable right here. We can fix that right here. The pressure, I've moved the negative sign, is this first term right here. Here's the area. The plate has height delta y and length negative 2y minus 4, and that's exactly what comes from this expression x right here. So we can multiply this stuff out and get this expression for the force, rho gy times 2y plus 4. These negative signs here and this negative sign have all canceled out. And I've made one other subtle change here. In moving from this expression to this expression, I have replaced delta y with the infinitesimal dy. Because in just a moment, of course, we'll take this expression for force, and we'll take all of these expressions for force, and we will integrate them together across the depth of the plate. And so when we do so, of course, our delta y turns into the infinitesimal dy, and we form the integral for the total force on the plate, which is found by integrating from negative 7 to negative 2. These are the ranges of the values of y, of our force expression right here. And now all that remains is to calculate the value of this integral. This rho and g, of course, these are constants, so we can move these right outside of the integral and write this as the constant rho g times this integral. Distributing the y across this binomial gives us 2y squared plus 4y. The antiderivative of 2y squared plus 4y is 2y cubed over 3 plus 2y squared. Then we integrate that. We evaluate that from negative 7 to negative 2. And I haven't forgotten about our constants, rho g, sitting in front. Doing so, evaluating at negative 2, subtracting, evaluating at negative 7, right here and here, gives us rho g times, well, this expression. So we get negative 16 thirds plus 8 minus negative 686 over 3 plus 49. All of those constants simplify down to 400 over 3. Right, and now I'll go ahead and fill in the values for these constants. Density of raw water is 1,000 kilograms per cubic meter. Acceleration due to gravity is 9.8 meters per second squared. Those are the values, but I have suppressed the units for this particular line. Multiply all of that stuff together, and we arrive at the sum total. 1,306,667 newtons. Remember, our goal is to find the force applied to this plate. I've rounded up, by the way, to the nearest positive integer, 667, in writing down that approximate answer. So that's the force on our triangular plate. If anything, this example gives us a good appreciation for the incredible force that water can exert, even at a relatively shallow depth. This plate, whose top vertex was only 2 meters submerged, has over 1,300,000 newtons of force applied to it. A significant amount. And the other takeaway, of course, is for this example, hopefully this example is clear enough and shows us how we can handle more general scenarios. Fluid pressure exerted on a plate which is of, say, trapezoidal shape, or which might be of circular shape. Maybe you want to calculate, again, the fluid force on the wall of a hydroelectric dam, or maybe you need to calculate the total force applied to a port or a doorway in a submarine submerged below the water. So I hope this example helps. And again, there are many more like it. We can adapt this method for different geometric shapes. Thank you.